Hello, we are David and Mila. We are presenting our Computer Science 3400 Data Preparation Techniques project, an analysis of popular movies from 1980 to 2019. Here we have a look at our data set before we do any work on it. It was taken from Kaggle, it has 12 attributes, and it compiles different aspects of the film industry from 1980 to 2020. Iteration 1, our data preparation and insights. First, we have the descriptors for qualitative attributes. And first, we have the descriptor for name. As you can see in this graph right here, man is the most used word. We have man followed by love and then by night. This is just words used in the title of the movies. Then we have our attribute descriptors for rating. Here we have, as you can see, R-rated movies have the highest count, followed by PG-13 and PG. And then we have the genre. So you can see comedy is the one that has the most amount of movies. However, in this data set, movies only had one genre. So even if in real life a movie had multiple genres, in this data set it would only have one. That's why comedy is the one that has the most, followed by action and then drama. And here we have a plot showing the movies made by one director. So you can see the amount of movies made by one director is around 2.6. However, he has a standard deviation of up to 3 movies. And this is just the amount of movies that they've made. And now here we have an attribute descriptor for a country. This is excluding the US, as the US is the one that produces the most movies by a lot. So we excluded it so we could see better what other countries made a big amount of movies. We can, after the US, we have England, followed by Canada. And then we have the attribute descriptors for company. Here we have the companies that make movies. As you can see, we have Universal Pictures with 377 movies, Warner Bros. With 334. And like that, we have a standard deviation of up to 60 movies per company. Here we have the attribute descriptor for date. As you can see, this is where the month that each movie was released. It's pretty even across all months. However, the month that has the most movies is October, followed by August.
And then we decided to look at numeric attributes, and the very first one is the score. So this is the score given to the movie by the critics. And we can see it's a very nice normal distribution. With the average score given to a movie of 5.5. Then we decided to look at how many movies were produced each year, and as you can see, the author only took about 200 most popular movies each year, except 2020, because we believe that that's when he stopped sort of doing this project. And we actually, later in the project, we decided to get rid of this attribute. We decided to get rid of this year because there's just not enough information to make any meaningful conclusions. However, we decided to keep this period of time because 1980 to 1984 contains a lot of classics, so we decided to keep it. Then we can see the attributes for runtime, and then we'll have budget and gross, and they're pretty much all analyzed the same way with a box plot and a violin plot. So as you can see, the average length of a movie is about 107 minutes, which makes sense. We have the shortest movie is 55 minutes, and the longest movie is 366 minutes. Then we have the distribution for budget. As you can see, $35 million approximately is how much the movie, an average movie spent on their production. We can see a lot of outliers, but they're not actually outliers. It's just a lot of big blockbuster movies that spent a lot of money, like Avatar or Titanic and stuff like that. And then the gross distribution is very similar to the budget distribution, with a movie on average making $78 million. And once again, a bunch of outliers, but they're not actually, because there's just so many big movies out there, and a lot of very small movies. Then we decided to look at some trends for our data set, and the very first one we decided to look at was how budget and gross sort of changed over time. As we can see, both of those attributes grew. However, the gross attribute grows much faster than the budget attribute, which means that movies tend to make more and more money over time without spending as much money on the actual production of the movie, which is pretty interesting. Then we looked at the correlation between budget and scores. We can see that the more money you spend on a movie, on average, you'll see higher scores for your movie, and that can be attributed to, more expensive equipment, more expensive effects, or better actors that you can hire. And the last insight we decided to look at is the correlation between budget and gross. And as you can see, basically, the more money you spend on making the movie, the more money you'll get from that movie.
After that, we have our work from iteration 2, where we did data cleaning and a supervised learning. Here, as you can see, we tested all the scaling techniques we saw in class on our data. We tested it on the attributes score, runtime, and gross. And as you can see, the C-score and log are the ones that we decided to use because they have the best results. This is because our data has a normal distribution. For part 2, we decided to encode some of our qualitative attributes. So you can see we decided to use a label encoder, as these don't have a necessary order, hierarchy, or anything. And we encoded the attributes rating, the genre, and country. And here you can see those attributes with the scaling techniques. Here we decided to go with the robust scaler, as it is the one that deals the best with outliers. Then we have part 3, handling the missing data and outliers. We decided to drop some of our attributes that we were not going to use for our analysis, like name, director, company, and date. Here you can see a snippet of our code on how we did it, and some information about our data set and how now budget is the one that's missing the most values. Now for cleaning outliers, we decided to use the interquartile method. Here is a snippet of our code on how we did it. For the attributes budget, gross, runtime, rating, and genre, we used the higher limit in the interquartile method, and for score, we decided to use the lower limit. Here's some bar plots for these attributes. As you can see, score, for example, has a lot of outliers, and budget and gross as well. We decided to deal with these with the interquartile method. And here you can see the graphs for runtime, rating, genre, and country. The only one of these attributes we decided not to do anything with was country, as it is not necessarily outliers, just countries that haven't produced as many movies or that have produced a lot of movies, like the United States. And here are new bar plots after removing the outliers with the method we used. You can see while the spread is a lot bigger and the variance is different, it has a lot less outliers for almost every attribute we have. And here's the one for score.
And then we also decided that we need a baseline strategy for dealing with the missing values. And we decided to look at the attribute gross, and it was very significantly skewed. So we decided to remove the missing values, to replace the missing values with the mean. And here in the plot, you can see in red is all the values that we replaced with the mean, so the attribute works pretty well, and in black is pretty much the gross attribute with the missing values. We actually did not use this method in the future, as we decided to remove the gross attributes with the supervised learning techniques, but we just figured it would be nice to see how this specific method works on dealing with missing values. Right, so then we went ahead and decided to use the supervised learning to remove the values for gross. And before we did that, we wanted to see which model would work best. So we decided to use KNN and linear regressor. The reason we're using regression and not classification is because the gross attribute is has continuous values as opposed to discrete values like yes and no. And our evaluation metric was our score. You can see on these box plots these are all the different models that we tried to use, and basically this is the KNN model with a variety of scaling techniques, and this is the linear regression model with the same scaling techniques. As you can see, on average, the KNN model does a better job at predicting values because its R scores are, like, on average higher than the ones for the linear regression model, because as you can see, these box plots, for example, they don't have the best R score values. So from these pictures here, we can see that min-max and these three box plots are sort of doing the best job because they have sort of the highest R values and the lowest spread. But I decided to look at the actual statistics for those box plots to decide on the best model we can choose. And the KNN model plus min-max scalar gave us the best R score of about 55%, and about 50% of its data was within 54 to 57.5%, which is a pretty good distribution. For the linear regressor model, we have an R score of about 55%, with 53 to 57%, once again, being the 50% of data. So from all of this information that we gathered, we decided to actually go with min-max scalar plus KNN regressor because, once again, as I said, on average, KNN just gave us better predictions. And this is what our plot looked like in black. Once again, it's the gross values before the predictions, and in red is the predicted values with the KNN plus min-max scalar. As you can see, the prediction worked pretty well. This is not the entirety of the set, it's just a small it's just a small portion of it, because you wouldn't be able to represent the whole data set in one box plot. In one plot, it would look very messy. And this is our distribution of the gross variable after we replaced the missing values. The distribution pretty much looks the same as it used before, so it has a slightly higher variance, but there's no outliers, and yeah, we think it looks pretty good. We decided to then check the prediction accuracy of our results by using the R2 score function. So we removed 30 values from the gross attribute, and then we predicted them and compared them to the actual values, and basically the prediction accuracy that we achieved was 27% with this method, with our model, and 27% is not the worst, it's not the best either. We believe that we could achieve better accuracies if we used some more sophisticated models than KNN, but it is beyond the course, beyond the scope of this course. So in conclusion, we analyzed data for movies, for popular movies from 1980 to 2019. We deal with the outliers via the interquartile range method, where we replace the outliers with either the maximum or minimum values. Then we explored how the data would behave if we replaced the missing values with the mean, and then finally we chose the supervised learning model, which was KNN regressor plus min-max scaling technique, which gave us the prediction accuracy of 27%. And we had a lot of fun working on this project, so thank you very much for your attention.